Hello everybody! Quantum mechanics has been the focus of physics education research since the 90s, and nowadays researchers no longer express doubts on the fact that it is fundamental for the culture and the awareness of the individual citizens and of the whole society. From surveys on teacher training, it emerged that most teachers, mainly with a degree in mathematics, often do not have a coherent reference framework for modern physics in general, and for quantum physics in particular. Moreover, the didactic path presented in textbooks is limited to a pseudo-historical presentation, which provides only a hyper-simplified explanation of the fundamental concepts, probably in an attempt to bypass the problems associated with the students' lack of adequate mathematical tools, but leading to deep misconceptions. This talk briefly describes the work of designing, testing, and evaluating a course for secondary school entitled The Elegance of Quantum Mechanics, presented in the last academic year. My presentation will be divided into three parts: the path, that is our didactical reconstruction of the subject; the experimentation, that is the online course The Elegance of Quantum Mechanics, together with its evaluation; the results obtained. And now the key point of our work. It is the physical theory with its interpretations that provides our physical image of the world. In our approach to research in physics education, therefore, we have to choose a reference theory in one of its formulations, identify the concepts of the theory, what it talks about, what the theory is able to talk about, and understand their relationships and their meaning within the theory. Make an educational reconstruction, taking into account not only disciplinary but also conceptual notes and also learning notes. We already have a quite effective reconstruction of classical mechanics, thermodynamics, electromagnetism. In fact, dealing with classical mechanics, we do not use the Principia by Newton as a textbooks, nor do we resolve complicated Cauchy problems. Nonetheless, the three principles of dynamics are well stated, and students work upon them with simple quadratic equations to solve dynamical problems. Analogous treatment received electromagnetism, no more complicated differential equation, but still Maxwell equations are at the basis of what is done in school. And now the question: is it possible even for quantum mechanics an educational reconstruction at secondary school level that, while greatly simplifying things, preserves its axioms and its theoretical structure? That's our aim, exploring the possibility of an educational reconstruction on quantum mechanics that starts from experimental data and induces the theoretical structure from which to explain phenomena, in complete analogy with what is done for classical mechanics or thermodynamics or classical electromagnetism. The aims are to get to a formal and theoretical construction of quantum mechanics. Why do we arrive at a specific mathematical structure starting from the identification and the subsequent description of a clear and rich experimental phenomenology? Why is the theory linear, complex, and probabilistic? To get to an identification of the complete axiomatic framework of quantum mechanics, in order to make it explicit and evident what the necessary mathematical tools are and the difficulties they could involve. Why do we need Hilbert spaces? Why the use of self-adjoint operators to represent observable, and so on, and also overcoming the learning obstacles concerning these mathematical aspects by carrying out different representations, in general as geometric as possible, for instance, working with the geometrical meaning of eigenvalues and eigenvectors. And now the schema of our path. From interference single quantum experiments, we induced the linear aspects of the theory, the necessity of a probabilistic description given with the Pythagorean theorem and not with the Borelian sets as usual in classical probability theory, and so on. In this way, we obtain a cascade reconstruction of the theoretical aspects of quantum theory. The experimentation. The activity, done online, was offered to teachers and students of the last 3 years of high school, 120 participants overall, from October 2021 to January 2022, through weekly appointments of 1.5 hours each. Lessons were integrated with slides, questions with Kahoot, and graphic examples with the GeoGebra. Here you can have a glimpse to the slides presented to students. The results. Course effectiveness was assessed by collecting and analyzing different types of data deriving from an anonymous satisfaction survey, 9 Google Forms given after each of the first 9 lessons, with a total of 38 open questions and 24 exercises, and 19 individual interviews aimed at investigating strengths and criticalities. Here some research topics emerged. This analysis allowed us to identify the reasoning that students commonly use in facing some conceptual issues of quantum mechanics. Students' difficulties and criticalities were found especially in dealing with spaces with more than 3 dimensions, with the concepts of self-adjoint operator, and concerning the confusion between states and operators. Difficulties also in the use of the Dirac notation in the calculation of the dot product between real or complex vectors. Difficulties in modeling. 30% of the students explicitly believe that are the quanta themselves that add up, and not the states. This is a confusion between the state of the quantum and the quantum itself. 45% of the students believe that only in classical mechanics it is possible to follow the evolution of a state, while in quantum mechanics it is not. This is a confusion between the concept of trajectory of an object and the concept of evolution of the state. We are now working on the refinement of our cycle to try to overcome these difficulties. And now the strengths of the activity. It was extremely useful for students, the graphic visualization of abstract concepts and the interactivity of the activities proposed with GeoGebra. But vectors with opposite direction are seen as different eigenvectors. It was also very useful the quick, fast, and immediate interaction of the just explained things through Kahoot. Almost all students had never dealt with complex numbers and matrices before. This was not found to be an obstacle in understanding. 69% of them became somewhat confident with metrics, and 89% with complex numbers. More than 80% of the students were able to express themselves appropriately about the characteristic aspects of measurement process in quantum mechanics, i.e. the probability of finding a certain outcome, the projection of vector state, and so on. And now some comments by the students coming from the questionnaire. Students 1. I really like the course because we also tackled it from a mathematical and not so popular point of view, and also because we started from things we knew. It was also nice that things were clarified, even for those who didn't know them, starting from things that are close to us and then broadening the concept. Students 2. I like the course because we started right from the basics and built the theory knowing what we were doing, without giving us formulas whose meaning we didn't quite know. Student 3, I also liked that you used quite easy terms, simple language. You never assumed that we already knew things before, because you introduced everything that was needed. More than 90% of the students were able to solve exercises of this kind, even if they were not previously already done. In conclusion, concerning the possibility of presenting a meaningful educational reconstruction of the conceptual and theoretical framework of quantum mechanics in high school, are students able to follow the mathematical aspects and use them in exercises? Are students able to conceptually link mathematics to physics? The preliminary results of this analysis pushes us toward a positive answer. And really many thanks for your attention.